Let's recap a bit of the special relativity topic before diving headfirst into the bigger, badder topic of general relativity. Space and time come together in the special theory of relativity, and energy and matter are intertwined in the energy-mass equivalence given by E equals mc squared. Take these two concepts and smash them together, and you'll get one general idea that combines the interactions of space and time with energy and matter: general relativity. And of course, who's responsible for this theory? None other than Einstein, who spent nearly another 10 years of his life just thinking, until he was able to come up with a better, more all-encompassing theory that took care of the plot holes that he saw in his own special relativity theory from 1905. In his report on the foundation of the general theory of relativity, Einstein stated that what special relativity disregarded, general relativity accounts for. This meant that while special relativity only explained motions and measurements of time under the constraint that objects are moving at constant speeds, it did not account for motions affected by acceleration, and of course gravitation. General relativity, on the other hand, incorporates these two effects. It just so happens that, as we mentioned previously, Einstein's theories, both of them, were and still are measurable, and they are supported by evidence. One of the greatest mysteries that helped validate the concept of general relativity was the fact that Mercury's orbit around the Sun had been observed to be precessing. This meant that the point in its orbit at which it's physically closest to the Sun, called the perihelion of orbit, changed by nearly 2 degrees per century. Newton's laws managed to account for all but 43 arcseconds of this change, implying that there was a very small amount of the change that could not be explained by the laws of physics that were accepted as the full and complete truth at the time. General relativity resolved the rest. Now, the three main implications of general relativity are that the presence of any sort of mass, whether it be big or small, minuscule or gargantuan, will warp the space around it. As a result, warped space will slow down the passage of time. The combination of these two concepts brings forth the most common phrase often heard in general relativity: the curvature of spacetime. Let's start with understanding the curvature of spacetime and how it depends on the presence of mass. Mass curves the fabric of spacetime. The more mass there is, the greater that curvature will be. It's this curvature that causes all the bodies in the universe to feel some sort of mutual attraction towards one another. This attraction is Einstein's way of explaining gravity, in a concept different than Newton's version of gravity. More massive objects have a stronger effect on the curvature of spacetime, implying that less massive objects must have a weaker effect. The motion of these less massive objects is thus governed by this curvature of spacetime caused by the larger mass. For comparison, let's see the curvature of spacetime around a usual star like our Sun and a neutron star, a highly evolved, very dense, very small stellar remnant. Einstein describes gravity as a deformation of spacetime around a massive object. So any objects that are traveling near these quote-unquote gravity wells will experience their motion having been affected by the curvature of that spacetime. In the case of even higher mass objects like black holes, spacetime is so stretched that even the imaginary grid lines forming the fabric of spacetime become parallel lines. The curvature of spacetime becomes more extreme with heavier and heavier objects. Now let's switch our focus to the concept of time slowing down as a result of the warping of space. Warped space slows down the passing of time. We also know that the presence of mass will warp the space around it. So it can be inferred that the presence of mass must also slow down the passing of time. The more mass there is, the more extreme the curvature of spacetime and the slower the clocks will run. For example, consider two identical clocks that are synchronized way out in space, far enough away from any other masses so as not to experience any relativistic effects. When one clock is moved to the Earth and the other is moved to the Moon, and both clocks are started and stopped simultaneously, the clock on the Moon will measure more time elapsed in the same time interval measured on the Earth, which measures less time elapsed. If both clocks were started at 3 o'clock, the clock on the Moon will record 22 minutes having passed by, while only 20 minutes were recorded on Earth. Because of this, time dilation in the realm of general relativity is called gravitational time dilation. In the confines of special relativity, the concept of time dilation, which goes hand in hand with length contraction, can be attributed to the fact that the speeds at which things can travel cannot exceed past the speed of light. Time dilation and length contraction are direct repercussions of this fact. According to general relativity, however, time dilation, and of course length contraction, is more drastic because the rate at which it happens will change depending on the clock's proximity to a massive object that warps the spacetime around it. For example, the GPS that we so heavily depend on works by broadcasting synchronized radio signals that provide information about the user's position, velocity, and time. Since these signals travel at the speed of light, GPS systems must take relativity into consideration for maximized accuracy. Otherwise, your GPS may end up not working properly, and you'll be forced to resort to using a physical map to get to where you want to go. Good luck with that. Now, just the same as objects are under the influence of the curvature of spacetime, so too is light. Light travels in paths defined by the curvature of spacetime. In flat spacetime, i.e. in the absence of mass, the shortest path that light will follow from point A to point B is literally just a straight line. However, if the surface is curved in any way, whether it's like a sphere here or like the gravitational wells we've seen forming around massive objects, that shortest path may not actually be a straight line. Instead, it'll be a curve. And these curves are called geodesics. We can see that light's path is altered near a massive object in this type of a scenario, where we have a star emitting light, but the light must pass by the more massive object like that white dwarf in the center of the image before reaching us, the viewer. Since spacetime is extremely warped near the white dwarf, the rays of light will be deflected because the curvature of spacetime will alter their path. So when the light finally reaches our eyes here on Earth, or the mirror of the Hubble Space Telescope, we'll perceive the star as being here rather than here, since that's where the starlight appears to be coming from. The second phenomenon associated with the effects of spacetime curvature on light is one in which a photon leaving a gravitational well will lose energy in doing so. As a result, the wavelength becomes longer since it's losing energy. If we think back to the relationships between wavelength, frequency, energy, and the speed of light, you'll recall that the lower energy waves of light have longer wavelengths and lower frequency. Now, this phenomenon is called gravitational redshifting. It looks something like this. If a lantern is held close to a massive object like a white dwarf or a neutron star and expected to emit high-energy blue light, its extremely close proximity to the star subjects it to extreme amounts of gravitational redshifting. So if the lantern is located slightly further away, it'll still feel the effects of gravitational redshifting, though not as much, and it will still be perceived as having less energy and a redder color than normal. So the closer the light is to a massive object, the more energy it will lose. This loss of energy determines how extreme the gravitational redshifting will be. In some cases, it'll be more easily noticeable than in others. In the next few videos, as we wrap up Unit 10, we'll see what happens when we fall into a black hole. How is that experience perceived according to general relativity? Stay tuned to find out.